We are approaching a massive wave of electronic waste. In the coming decades, millions of tons of batteries from electric vehicles and personal electronics will hit the scrap heap. These dead devices are essentially sealed vaults. They hold highly valuable, critical minerals like lithium, cobalt, and nickel trapped inside. This puts us in a bind. We are rapidly draining the Earth of virgin materials, taking a severe human and physical toll to extract them, while simultaneously piling up mountains of toxic refuse. Simply burying these spent cells in a landfill is out of the question. To survive the renewable energy transition, we must figure out how to crack open this waste and finally extract the wealth trapped inside. Gathering up all those aged batteries presents a massive logistical nightmare. Years of constant charging and discharging severely degrade their internal physical structures. Degradation creates hazards. Sharp lithium dendrites form and pierce the internal separator, dropping the safety threshold to 150 degrees. An uncontrollable chain reaction takes over. The failed cell spikes to 1,000 degrees, igniting adjacent cells and venting toxic hydrogen fluoride and carbon monoxide. Large-scale energy storage facilities have gone up in flames, requiring weeks to control because of these exact dangerous chain reactions. Handled improperly, these concentrated energy sources become active threats. Battery recycling isn't just waste management, it's a high-stakes hazard mitigation operation. Engineers have to safely stabilize these units to access the valuable materials within. Over on the factory floor, engineers have developed 3 distinct eras of recycling technology to safely breach these cells. The oldest approach is a brute force method called pyrometallurgy. Operators throw the batteries into a furnace and melt them at 1,600 degrees Celsius. This recovers heavy metals like cobalt and nickel, but it permanently destroys the lithium and aluminum, leaving them trapped in the leftover slag. The current industry standard is hydrometallurgy. Instead of melting the batteries, machines physically shred them down into a highly concentrated powder known as black mass. Black mass runs through a liquid leaching process. It recovers over 95% of cobalt and nickel and 90% of lithium in pure streams. But these extraction rates come with a steep cost. The process uses harsh acids, generating significant volumes of toxic wastewater. While hydrometallurgy isolates the metals beautifully, its heavy chemical footprint means it cannot be the ultimate clean solution we need for the future. Companies only recycle batteries if extracted metals are worth more than processing costs. Older NMC batteries generate high profit margins due to valuable cobalt and nickel, but newer LFP batteries use cheap iron and phosphate. Their extracted value falls well below the processing cost. Standard recycling methods destroy the battery to extract raw elements. Because those raw elements in LFP batteries are inherently low value, they are currently unviable to recycle, meaning millions of them could sit in landfills. This diagram outlines a newer solution called direct recycling. Step 3 bypasses the chemical breakdown phase entirely, preserving the physical components, the cathode and binder, instead of melting or dissolving them. By utilizing a solvent extraction process with supercritical carbon dioxide, direct recycling rejuvenates the cathode material directly. Skipping the energy-heavy refinement process saves up to 90% of the energy required. Direct recycling ensures that the recovery of all battery chemistries, even the low-value ones, is both economically and chemically feasible. Pulling back to the macro scale, those streams of recovered materials are pressed directly into new electric vehicle cells. You burn a gallon of gas once, and it's gone. The metals inside a battery do not degrade or burn away. They can be recovered and reused for centuries. We are moving away from an economy reliant on continuous, risky foreign extraction and toward one built on perpetual circularity and resource independence. This chart illustrates the concept of peak mining. Total mineral demand keeps climbing, but watch the line for virgin mining. As efficient recycling scales up, virgin extraction peaks in the mid-2030s and then falls as the recycled supply meets more of our needs. If we maintain this level of efficiency, the mining of these minerals becomes a one-off effort to build our initial stock. The millions of batteries retiring by 2050 could eventually provide the majority of our raw materials, significantly reducing our reliance on new mines. Once the physical risks are managed, these batteries provide the feedstock for domestic energy storage systems. This chart compares the environmental impacts of virgin mining, the tall gray bars, against direct recycling, in red. Focusing on climate change and human toxicity, we see significant drops for direct recycling compared to both mining and older methods. The end of a battery's life cycle is a pivot point. We are training our industrial systems to treat waste as the precise raw material needed to manufacture the next generation of power storage.